Hello, Year 10. This is Mr. Radmel, bringing you the Triple Science Particles and Radiation 2, Lesson 5. Right, let's get going. So, the driving question today is, how can radioactivity improve your health? And your starter question is, which situation would be the most dangerous? An alpha source inside your body or a gamma source inside your body? A or B? What are you going to go for? So, can you write down the driving question? Pause the video. Okay, it is in fact an alpha source inside your body. So, funnily enough, an alpha source in the same room as you, you're pretty much safe because alpha can be stopped by air or paper. But if it's inside your body, it's going to cause you a lot of damage. Whereas a gamma source inside your body, as we'll learn this lesson, is not that dangerous at all. So, let's just quickly talk about two key ideas when it comes to radiation. Firstly, ionisation. So alpha, beta, and gamma particles that come from the nucleus are ionizing. This means that they can knock electrons off really easily. And if they can knock electrons off really easily, they can do that to the atoms which make up your DNA, which can cause damage, kill cells, or cause mutations in cells, which can lead to tumours and lead to cancer. So alpha, beta, and gamma particles are all ionizing. Alpha being the most ionizing, gamma being the least ionizing. Now also, alpha, beta, and gamma particles have different penetration. In terms of alpha, which is the most ionizing, can't get very far. Beta is in the middle, so can get through paper but can't get through aluminium. And gamma is the most penetrating and can only be partially stopped by thick lead. So gamma is very good at penetrating, many materials, many hundreds of miles of air, for example. Okay. So how do we go about using radioactive sources? We're going to go through a few examples today, starting with the smoke alarm. So a smoke alarm, which hopefully we all have fitted in our houses or our flats, makes use of an alpha source. So it's a very weak alpha source, giving off alpha particles periodically. And those alpha particles in the smoke alarm are ionizing the air, which causes a current to flow, which is detected. Okay, so the alpha particles make a current flow through ionizing the air, and that's detected by the smoke alarm. Now, if smoke gets into the smoke detector, that disrupts the currents because then the alpha particles are blocked and ionizing the smoke particles, so the current decreases, and the smoke alarm detects that change in currents, the current decreasing, and sets off the alarm. So that's a use of an alpha source for a smoke detector. So thinking about why an alpha source, why not a gamma source? Why would a gamma source, answer the question, why would a gamma source not be suitable for a smoke detector? A, B, C, D. Which is the correct answer? Why is a gamma source not suitable for a smoke detector? Pause the video. Okay, it is in fact B. Gamma is too penetrating and wouldn't ionize the air. So alpha is used because it's not very penetrating and it will ionize the air to create that current. And then also, of course, won't be able to penetrate the smoke either. Okay. So next up, how do we make use of a beta source? Well, one example of making use of a beta source is controlling the thickness of either you find this in paper mills or you can find it in factories making sheet aluminium. Okay, so beta particles can penetrate paper, and let's stick with paper. So beta particles can penetrate paper, but some of the beta particles will be absorbed. The thicker the paper, the more beta particles will be absorbed. Now, this can be detected and fed back to the rollers. And this is used to control the thickness of the material. So if the material becomes too thin, that means more beta particles can get through, and the detector tells the rollers to make it thicker. If the paper's too thick, then less beta particles can get through, more are absorbed, and then the detector tells the rollers to thin it out a bit. Okay, so there's an example of making use of a beta source. So this time, using these ideas, which of these statements is not correct about controlling thickness? Which one is the porcupine, which is East London slang for lie? Pause the video. Okay, it was in fact C. If the paper is too thick, then more beta radiation would be absorbed. Okay, so next up. So making use of a gamma source. Now, a gamma source is used in what's called a medical tracer. This is where a gamma source is actually injected into a patient. And that means that you've got a radioactive isotope inside of you giving off gamma radiation. Now, gamma, remember, is the least ionizing, the least harmful of the nuclear ionizing radiations. So it doesn't cause you a lot of harm to have a source injected inside of you. And then what doctors can do is they can track the gamma source as it moves around your body using, something similar to a Geiger counter. So doctors use radioactive chemicals called tracers for medical imaging. Certain chemicals concentrate in different damaged or diseased parts of the body, and the radiation will concentrate there as well. So doctors, for example, can identify a tumor inside the body. Radiation detectors placed outside the body detect the radiation emitted. When a radioactive chemical is used in this way, it is not normally harmful because it has a short half-life, more of that to come, and so it decays before it can do much damage. Emitters of gamma radiation are used because this type of radiation will readily pass out of the body and they are less likely to be absorbed by the cells. Another good example of this is doctors examining how quickly kidneys can get rid of substances, because that's what kidneys obviously are there for, to remove harmful substances from the body. And so tracking a gamma emitter as it goes into your kidneys and then exits your kidneys is a good way of doctors to study kidney function. Okay, so medical tracers. Which statement is the porcupine? Pause the video, please. Okay. So it's in fact A gamma source is used because it can easily leave the body and be detected. Now, if it was an alpha source inside your body, that would be wholly inappropriate, wouldn't it? Because firstly, it'd be more ionizing, so it would cause you a lot of damage inside your body. But also, doctors wouldn't be able to detect it. It wouldn't be able to get through the first layer of tissue. Okay, so we've talked about, last example, just throw this one in. So gamma rays are also very useful for sterilization. Okay, so destroying microbes on food and on medical equipment. Now, what's really useful about using gamma radiation is that you don't actually have to heat anything up. So one extra use of radiation, I'm just going to throw in there, is gamma radiation to sterilize, to kill microbes on food and also to clean medical equipment. Okay, so we've talked about why three different sources, gamma, beta source and a alpha source, why those particular sources are appropriate for the use. We're now going to throw in idea of half-life as well. So what kind of half-life should we be using with our sources? So firstly, let me remind you what half-life is. It's the time taken for the radioactivity of a substance to half. Okay, so let me give you an example. Let's say we've got a radioactive substance called bluium. I've made that up for the sake of a diagram. And bluium, when it decays, it becomes radium and then gives out a alpha, beta, or gamma. Doesn't matter which. So if the half-life of bluium is 2 minutes, how many bluium atoms are left after 2 minutes? Well, the answer, we've got 16 in total, would be 8. So after 2 minutes, 8 of the bluium atoms have decayed into radium atoms. How many bluium atoms will be left after 4 minutes? So after another half-life, so it's 2 half-lives now, you would end up with 4 bluium left. And how many would be left after 6 minutes? The answer to that is, the answer to that would be, of course, only 2. So every half-life, half the number of atoms decay, the radioactivity decreases by half. Let's put this in a graph. Have a look. Okay, here is the radioactivity of a source starting at 80 counts per minute. What is the half-life of this source? A, B, C, or D? Pause the video, have a look, have a think. Okay, so it starts at 80, so after one half-life, it's going to be 40. We go across to the line and down, we see that it takes 2 days to get to 40. So therefore 2 days is the half-life of this substance. So how does this fit in with uses of radioactive isotopes? Well, for a smoke alarm, you don't want to have to keep replacing the radioactive source in there. So you need a long half-life. That means you don't have to keep on replacing that alpha source. Again, for thickness control for aluminium or paper, you also need a long half-life, so there's no need to replace the source. However, if you're using a medical tracer, then you want one with a very short half-life. Technetium-99, for example, is 6 hours half-life, which is a commonly used gamma emitter for a medical tracer. And the short half-life means the radioactivity quickly decreases to a safe level. Okay, so let's bring all these ideas together, please, Year 10. So for number 1, can you describe some uses uses of sources of ionizing radiation? Sentence starter in red. Then, can you explain explain what happens, how radiation is used for each of those examples, please? So what they are. And then for number 3, for each of the examples, medical tracer, paper thickness, smoke detector, explain why the type of source is suitable and what a suitable half-life would be for each source. So you're explaining what happens with each example for explain, for number 2, for green, and for yellow, bring in ideas of penetration, ionization, and half-life. And then for combine, I've put in a numerical question for you based on half-life. Okay, pause the video, please. Okay, let's go through some answers. So firstly, examples you can come up with of uses of radiation. You've got the smoke alarm, you've got the paper thickness, you've got the medical tracer, and you've got the sterilization of food and sterilization of hospital equipment. Right, then explaining how they're used. Well, a medical tracer is a gamma source injected into the body, and a camera or Geiger counter is used to track the source as it moves around the body. For thickness, radiation is used to detect paper thickness by using a beta source. A Geiger counter is linked to the rollers and keeps the thickness constant. And then radiation for C, radiation is used in smoke detected by an alpha source ionizing air and smoke between two metal plates. So for a medical tracer, why do we use a gamma source? Because it can easily penetrate the body and be detected. And a short half-life is needed, so the radioactivity quickly decreases to a safe level. Why is beta used? Well, it's because the thickness of the paper affects the absorption of the beta particles. A long half-life would be needed, so the source does not need to be replaced very often. And for a smoke detector, because alpha is very ionizing, ionizes air easily, and a long half-life is needed, so the source doesn't need to be replaced that often. And then for combine, well, if you're halving the activity every 6 hours, 24 hours is 4 half-lives, so you halve it 4 times, get 6.25% of the original activity. So now can you copy and complete the plenary sentence? And remember year 10, there's now a 10 question multiple choice quiz to do. Thank you very much for your time. Stay safe. I look forward to seeing you the next lesson.